I'll just give a recap on what we have done so far in practical. Initially, we have done how to scrap data from internet. Then, using those scrapping data, we scrapped it from multiple pages of the website also. If it is have more pages, scrapping in the entire data also we have studied and we have done in practical. Then we moved on to linear regression, and we moved as deep as possible like linear regression, multiple linear regression, and polynomial regression. We did everything. Then we practically see where the overfitting will come into play. We increase the polynomial regression up to degree 20 in the previous overfitting practical exercise and see how the overfitting will help us. But even the degree 20 in that particular example also is not having that much effect on our particular data set, right? So in this exercise, as a continuation, what we are going to see is how we can, if the overfitting is there, it means that my model parameter is actually mug upping the training data. So what we are going to do is we are going to study hyperparameter tuning, hyperparameter tuning in this particular practical class, right? Hyperparameter tuning is one of the most important thing. Then I need to reduce the error. One kind of what I can do is I can change the model or I can estimate the hyperparameter. What by hyperparameter what I mean for linear regression I have hyperparameter as my feature weights. I have beta one, beta not, beta two, everything. Those are actually my hyperparameters through which I can have a control. Hyperparameter is nothing but the model parameters in which the programmer or the developer has a control over it. That I call it as a hyperparameter. Okay, that's what we are going to discuss in today's class and how that hyperparameter is actually being estimated and what are the different type of models we can actually go for this particular thing. Right, that is what we are going to see. Right now, what we are going to do is we are going to take some machine learning data set and using that particular data set, I'm going to estimate how the particular value is changing with respect to some independent values. The normal linear regression I'm going to do. Then I'm going to estimate how this linear regression is going to behave with respect to some other models. I'm going to take another model and compare both the models and say which is actually the better model. And then we are going to use something called as grid search. Grid search is actually a package which is actually used to say as how the hyperparameters can be tuned and find the best parameter. That is grid search CV is actually a library function that will help us to say how a particular hyperparameter value can be used as a best score in our model. Right, the best score can be identified through the R squared score, that is coefficient of determination. If it is closer to 1, it means that my model is working good. That is what the thing we are going to see here. In this, we are going to see many different types of regression also. We know only linear regression, multiple linear and polynomial so far. In this class, we are going to add some more regression concepts also, right? So, what is the thing I'm going to do? Just what are the things to import? I'm going to import from sklearn dot linear underscore model. Import linear regression. So just the same. First, the thing is we already know that linear regression is going to be done, and I'm going to teach you many different types of regressions available here, equivalent to linear regression, and how cross validation can play a major role in improving the hyperparameter values. That is what we are the ultimate motto of this particular practical section, right? So we'll go and say take that. Next, I need the data sets to be downloaded. To maintain this thing, I have taken a data set that is already available in the packages of machine learning. So, inbuilt data set I'm taking. So, I take it from sklearn dot data sets. Why? Because if I take a data set and ask it to behave with respect to cross-validated scheme or overfitting scheme, it may or may not fit, because if I randomly take some data set, I may not assure that it will behave in the way what I actually need. I want a data set which is actually behaving more overfitted for one particular model, and then I want to tune the particular model and change it in such a way that for some other model parameter it gets improved. Like that, I have to change. So I just take an inbuilt data set which has such a characteristic. So we can understand clearly how it is going to behave, right? So on a scale and a data set, I'm going to import the most famous diabetes data set. I'm importing the diabetes data set. Next, as usual, I want a training and testing. So from sklearn dot model selection, import train underscore test underscore switch. Sklearn model selection, train import train underscore test underscore switch. I just run it to ensure that the packages are existing. Yes. And what I do is I go for the particular things what I actually require. I want to do cross validation, so I take the cross validation metric also. On scale and learn dot model selection, import cross underscore val underscore score. This is actually the package which is used to perform cross validation, right? That is from scale and dot model selection, import cross underscore val underscore score. So this is the packages what we require. Now we can go and proceed with how the data set is going to behave, right? We go to the diabetes. Let us see how diabetes is going to perform, right? Diabetes data set. I just have diabetes comma target. I'm going to assign what is the input and what is the target variable. So the input variable is going to be taken since it is a predefined data set already available. It itself says what is going to be the input, output, everything. Okay. So I just say return underscore x underscore y, and it itself says what are the inputs and what are the outputs. We don't need to specify and these particular data are input and this particular data is output. That is not required because it is already an existing data set. So it itself will have a thing that x has a bunch of values which are taken as inputs and y will be the target variable. Right? We can also visualize how the x and y is actually being by using the head function. Right? Next, convert it into data frame pd dot data frame, that is converting that entire data set into a data frame for operations using NumPy. So everything is converted into a data frame. PD is not defined. So I go up, import pandas as P. Yes. Next, I separate the inputs and outputs. I separate the inputs and output. I take X as a capital X as an input, and X is going to be the value which is going to be taken here. This is all the X values will be going into the diabetes. Y value will go to the target. So I take X as diabetes, which is a data frame now. So once it is converted into a data frame, I can do all the NumPy array operations in that particular uh, variable object. Right? So X is equal to diabetes and Y is equal to target. Now I assigned. Now everything is set. Inputs are ready. Now I want to do setting up of training and testing. Set up, train and test data. Setting up is very easy. As the same thing what we do for all the models. I just say x train comma x test comma y train comma y test is equal to train underscore test underscore split of. We will be usually giving 75% for training and 25% for testing. Let us give the same thing here. X comma y, that is the input data. X is the input and y is the target. S comma y, and what is the test size? Test size is going to be 0.25, meaning that 25 percentage of data will be for testing and 75 percentage of data will be for training, right? Comma random state. Can give the random state in such a so that I can get a random shuffling or random sampling of data, and I can give any number here. Let me give 27. Right? Some number I can give, so it is actually a random state. So depending upon that, randomly my data will be sampled and given for training and testing. That is 75 percentage for training and 25 percentage for testing. Now what I'm going to do is, now I can do a linear regression task for this. Just to put linear regression function and fit and see how the values are, how my linear regression equation is. So I just take, actually I already have the linear regression model included. I use that model. I take LR is equal to linear regression. Linear regression function is taken. Now I say LR dot fit of, I can fit X train and Y train, and say what is the equation. That's what I'm going to do. So X train comma Y. The X and Y values will be fitted here. Right now I got the values. I just print and see what will be the LR value. Right, I just see LR dot coef, LR dot intercept. Yes, it is printing for all the variables I hope. So this is the thing we have. Now what I have to do is, now this model is ready. Now for this model, I have to do a cross validation scheme. Because if I print LR, it is actually giving me a set of variables which allows cross validation. How I am saying it allows cross validation is, if it is saying copy of X, I'm saying it to true, means that for training and testing, I can have duplicate data also. Right? When I do cross validation, I can ensure that at least minimum 5 folds cross validation will be available. Now I have to do cross validation for this linear regression thing. So what I do, I take another cell, just I define a cross validation function. The same cross validation function, like in the previous practical exercise, we use a same function for pre-processing of infinite values and NA values. Here we use a function which can do cross validation. Right? I take def cross validation. Is called validation. This function is actually a function which will take the input as the model. I take the input as a model. Whatever here my model is LR, right? I take and the model. So from the model, what it should take is, it can take X train, Y train, everything it can take from the model. So I take scores is equal to cross underscore val underscore score of model, comma. I have the X train and Y train values present on the upper thing. Everything it can use. So I can take X underscore train, Y underscore train, and I can say how many cross validation, how many fold cross validation. I keep here 5-fold cross validation, right? I keep here 5-fold cross validation, and the cross validation should be estimated through what scoring is. I say R2 through R squared estimate. My cross validation results should be validated. So this is actually the thing. I take the model, I take the X train values, I take the Y train values. I'm going to use 5-fold cross validation, and the cross validation results are going to be estimated through R2 metric. Next, what I do, I just print the mean cross validation, right? Mean CV score. So CV mean will be taken. CV mean is nothing but NP dot. We have all the scores available. We have 5 folds. If 5-fold in the sense, the entire data will be divided into 5 different blocks, and in each block we'll have a common number of items. Right? I just say NP dot mean of scores. For each different block, I'll be getting a score, and that score mean will be taken. That is CV mean, and standard deviation also I can take. Print STD. That is NP dot STD of mean of scores. Both I take and then I put. Right, this is actually the case. Now for this LR, let me apply the cross validation and see how the results are going to be affected, or how the results are being there. What is the mean cross validation? That is mean score for R2 to the model, that is LR. I give LR to it. The exact validation cross validation. So I have to run this. And I come and run this cross validation. Cross validation.
Sir, in the text train and y train are not defined
Yes, that's
in
what I understood. R2 is okay. X train and Y train, it is actually taking from the upper thing, right? I have defined it globally. See this thing. It will be directly taken, right?
okay.
The thing is, R2 is not defined, I hope. That is this R2 value. I think this should be in. I should try this. First, I put this in double quotes. Then I run again. np dot std, of course. And here cross validation of np. Such np is not defined. Import numpy as np. Yes. Yes. So the cross validation mean, this cross validation mean is with respect to the R squared metric. The R squared metrics, the coefficient of determination should be as close as possible towards plus 1, but it is actually 0.47 for the linear regression model. The linear regression model, it is giving me 0.47 result for the diabetes data set, right? So now what is our role is we need to tune our hyperparameters. Now we have to think what are our hyperparameters. Generally, we will be touching only the model weight, that is beta 1, beta 2, those weights we will be touching. So we say that that weight is actually necessary for tuning this. More than this, we have another thing called as the learning rate, right? That is alpha value. How the alpha value can be tuned in such a way that my model accuracy can increase. So that is what we are going to study here. And for studying that, we need to understand what are the other models that can give even better score than this particular linear regression model, right? So what is the next thing we are going to see is, let me put a uh, comment here, that is this is linear regression model. This is model 1, that is linear regression model. Next, what I'm going to take is the new regression. What we are going to consider here is regression model. Right? Ridge regression is so from linear regression. I can import it from sklearn dot linear and linear underscore model. Import ridge regression. Import ridge. Let me search here. Ridge. Ridge regression is also there. Let me put ridge because capital. Yes, in my sklearn dot linear model, import ridge. Right. This ridge is actually somewhat different. For this ridge, we need to set what is the alpha value. The default alpha value, what it will usually take is 0.5, right? But we can also increase or decrease the alpha value. Alpha is nothing but, I mean, the learning rate, how the model is going to learn and how fast in each iteration the model should learn. That is what the alpha value. I can also set the alpha here. Ridge of, ridge is equal to ridge of. Now I say alpha is equal to 1. I set alpha is equal to 1. In most real-time cases, we think alpha is equal to 1 is not good. But let us see how ridge is actually behaving when alpha value is equal to 1. Even I can set alpha value is equal to 100 or 200 also. But let us see what the ridge is going to have in this particular value. Right? I give the x train and y train here. X train comma y. That is fitting with ridge model. Or we can also fit like, instead of fitting like this, we can also fit like ridge dot fit off. X train comma y train. So this is the ridge model that is giving us the result. Right now, ridge is spread. Now let us run the cross validation with respect to ridge model and see what is the best R squared metric for ridge model. See, for ridge model, I'm getting 0.38, where for linear regression I'm getting 0.47. But ridge is actually closely aligned with the alpha value. With respect to the change in alpha value, this ridge model will perform better, right? Now, what we need to understand is we need to understand what is the background of ridge regression, right? So it is actually similar to linear regression only, but mostly aligned towards multicollinearity. What is that multicollinearity in the sense? There will be more predictive variables, and in those multiple predictor variables, more correlations are available, right? In linear regression, we'll be usually saying, right, when it is goes into multiple independent variables, the independent variable correlation should not be maximum. If the independent variable correlation is maximum, then the linear regression will not perform well. That is the thing we will be saying in the multiple linear regression. But we cannot say that the independent variable correlation will be zero always. At least some kind of correlation will always exist in multiple linear regression for the independent between the independent variables. If those correlations are more and not controllable, then the regression model which actually suits you is ridge regression. Where if I have multiple independent variables and the correlation between those independent variables is high, then I can go for this ridge regression, right? This ridge regression is also the thing which performs something called as L2 regularization. So L2 regularization is nothing but a method which is used to reduce overfitting. When you see the overfitting models, the main thing what we do for overfitting initially is cross validation. This ridge regression is actually one of the very good method to avoid overfitting because it has a capability to come out from those correlations between the independent variables itself because it is regularized, and this regularization will help us to make the model go without overfitting. It will train the model without overfitting. So what is the disadvantage and why ridge regression is not widely used is this ridge regression will suffer when the model is not having that much correlation between the independent variables because ridge regression goes with the assumption that it suffers from the correlation between independent variables. Whether it has the correlation or doesn't has, it assumes that correlation is there, and because of that it will make the model to be stringent, and the model accuracy will always be low because it provides more bias onto the model, right? Because if variance is high, overfitting will come, so it put more bias onto the model, and because of that the ridge regression will be suffering from those accuracy constraints and it will not be that much accurate. But so only ridge regression is actually playing with alpha. Based on the alpha value, this value, that is the R square metric of ridge regression, can be improved. For alpha is equal to 1, it is actually giving a value less than the linear regression. Once I increase or decrease the alpha value or tune this alpha parameter, I can find that this ridge regression is performing better than linear regression. Finding the alpha value or tuning this alpha parameter is not an easy task. We need to take the entire data set, analyze it, and find the best value for this alpha. So that is called as alpha tuning. We need to tune the alpha so that the best value can be obtained. Right now, that only we are going to see what will be the best alpha value for ridge regression. We are going to do. Yes, now we are going to do that. What is the disadvantage of ridge regression? Since it put more bias onto the model, the accuracy of the model gets affected, right? So what we have to do, we have to work on the alpha value. We need to tune the alpha value and make the ridge regression go good, right? So now let us go and tune the alpha value. That is, find the optimal alpha value. We want to find the optimal alpha value for this ridge regression. So it is actually a trial and error method. where we take a list of all possible alpha values what we actually require. Whatever alpha values you need, you can take. That is the model learns. That is, we set alpha value to be 0.001, 0.01, 0.1. You take 1, and anything. If you want how many values, you take all the values, and you put all the values over here and find the best value. Right? I take 4 different values. Next, I define another variable, that is param grid. This param grid is one of the parameters in grid search CV function. Right? Let me write grid search CV function and show you what is the use of this param underscore grid. Let me write the grid search function and say what is param underscore grid. That is, I'm going to write grid search CV. Grid search CV is actually a function which is actually used to perform cross validation schemes for a list of many folds. If I want to do those kind of things using trial and error method, grid search CV method is actually used. So I need to import grid search CV package also. So let me import that, or I already have model selection underscore cross underscore val underscore score. Let me try and try here why the grid search is actually. Yes. The grid search CV of, I go for the estimator. What estimator you are going to use? My estimator is going to be ridge model. The model name you have to give. What model you are going to use? You use. My model is going to be ridge. Ridge model you are going to use, which is a regularization technique also. And what is the parameter we are going to tune? That is, the parameter going to be tuned should be given in something called as param grid. This param grid function should be given to the should be given the parameters which are going to be tuned for that particular model. I have taken the ridge regularization. For this ridge regularization, what is the parameter that is going to be tuned is alpha. So I just say param underscore grid. So just substituting these values over here. Next, what is the scoring we are going to estimate? Scoring is R2 estimate, and I give verbose some default parameters and the number of jobs, parallelization jobs equal to minus. I think grid search, name grid search CV is not defined. I think I need to import grid search CV. Let me search here. Yes, from sklearn.grid search, import grid search CV. Take this, I substitute it. Okay. Just a minute, let me find out how to include that grid search.
Sir, Akshit kept something in chat box about that.
From sklearn. Okay, from SQL under model selection, import grid search.
Yes, sir.
Yes, I'll try that. Import grid. Import grid search. Now I can use from learn dot model selection. Import grid. Yes. Thanks. So it is actually the research series working. Now what we are going to do is we are going to estimate with respect to our training and testing values. Now grid search CV parameters are set. Now we will see the grid search will fit the grid for the our one explain and expressed values, and we can find the result. Grid underscore result something. So grid result will be grid dot fit of explain command right, and I print the best score. That is what that is the best model parameter in the cross validation result will be displayed. Grid underscore result dot best underscore score. So the best underscore score underscore will give me the best score model, and then I print the best parameters also. Print parameters will give me the alpha value. Print best parameter. Print underscore result dot best underscore parameters. Fitting 5 folds for each of the 4 candidates. So that is there are 5 folds, and in each fold there is 4 items. Totally 20 fits are actually being obtained. So the best score obtained here is 0.47 with alpha is equal to 0.01. Right? So for the ridge regularization, if alpha value is set as 0.01, I'll be getting a best score as 0.476. This is called as model tuning, right? I'm identifying the best value for alpha, and out of these 4 values, 0.01 is actually giving me better result. I go back to ridge regression. I set it to 0.01 and let us check whether it is at least closest to this particular value. It is actually randomly selecting, but let us see whether it is at least closest to 0.476. So now alpha value is changed. You see, when getting it 0.476. So when alpha is there. So this is what identifying the parameter values. Instead of directly working on the features, or instead of changing the model exactly, we can also find what is the parameter which actually affects the learning parameter also. So this is one of the way to identify alpha. And whether only one regularization is available in regression? No. Apart from ridge regression, we have others also. So have everyone completed up to this? Or shall I want to move up or
Yes,
down?
sir.
Yes. So I think this is Abhiram voice, right?
Yes, sir.
Yes, Abhiram will complete the time. Others, have you completed up to this? Yes, Pavani also.
Yes, sir.
Yes.
Yes,
So
sir.
the
Sir,
final regression, yes, yes, Narasimha. Yes, Narasimha.
sir, verbose and n jobs means what, sir?
Yes, verbose and ethmos are actually parameters. I'll just search here and Google it. I also don't know. And when you ask me, I search here and say because I still don't know what is verbose.
Okay, sir.
Verbose in research you asked, right? Because I just take research and see. N jobs I can say n jobs is with respect to the number of jobs that to be parallelized. And I go to this link. Hope you can see this link, right? This is scikit-learn.org. In this link only I'm saying. You can see this link, right? Yes.
Yes, sir.
The higher, the more messages. Compute if greater than 1, the computation time for each fold and parameter candidate is displayed. If greater than 2, the score is displayed. The fold and candidate parameter indexes are also displayed together with the starting time of computation. Controls the verbosity. The higher, the more messages. I hope the verbosity is nothing but more information. If it is greater than 1, we'll be getting the computation time for each fold and parameter candidate is displayed. What we are getting actually, we are getting computation time is there here. Okay, that is elapsed 1.5 is there, and the number of parameters also displayed. Let me take it to verbose is equal to 2, and verbose is equal to 2 also. I'm getting, or when verbose is equal to 1, what is the difference? I couldn't find any that's different. I look into it, Narsima. Even I don't know what is verbose.
Okay, sir.
Yes, I look into it. Here it says that if it is greater than 1, it is displaying the computation time for each fold and the parameter candidate. If it is greater than 2, the score is displayed, and it is greater than 3, the fold and candidate parameter. Right. So these parameters we rarely use, right? So we need to look into it. I look into it and I'll message you.
Yes, sir.
Yes. So the next model with respect to another regularization is lasso regression. This is also one of the rarely used regression, but will be very nice.
Sir, one small doubt.
Yes.
Sir, in printer you have used grid result dot best score, no sir?
Best score underscore yes.
Sir, from where we have took sir this one best score and best params, sir.
Yes, this grid result is actually when we are fitting it. For example, if I want to say you very clearly, when I take a linear regression, LR is equal to linear regression of. Then you say LR dot fit of x comma y. After doing that, you are saying LR dot coef underscore, meaning that you are taking the coefficient of the particular value. Then you say LR dot intercept underscore, meaning that you are taking the intercept value. Because after fitting, the linear regression object will give you coefficient and intercept. Similarly, when you do grid search CV, when you fit it with x and y values, you'll be getting the model parameters. The parameters that will be obtained after fitting the grid searches, you'll be getting best score, best params. And if I want to say you more thing about this, see, these are the values you will be getting when you finish the grid search. When you fit the grid search model for your x and y values. Am I making it clear?
Yes, sir.
Yes. So let us go for lasso regression. May now not much difference to regularization is also another method for decreasing the particular overfitting criteria. How can I decrease overfitting and how can I make the model to work good? Exactly same as ridge regression, but a different way of regularization. Right? So I make the same things from sklearn dot linear underscore model import lasso. Next, what I do, do the same thing what I did for ridge regression. I do here also. So lasso is equal to, I take a variable lasso itself. Lasso is equal to lasso of alpha. So here both regularization techniques will work based on the alpha value only. Still, I was actually having a doubt on how to fix the alpha value. Just I'll pick alpha equal to 1. Then I will clarify my doubt by using the grid search CV. I'll go apply lasso also to grid search CV and find which is the best tuned value for alpha. So I fit lasso dot fit of x, x name, comma, y. So lasso is fit now, and I can now see that how lasso value is going to behave with me. I'll do cross validation for this validation of lasso. So lasso is giving me a mean R2 value as 0.35. If you go above and see before, ridge regression gave around 0.36 when you have alpha is equal to 1, and normal linear regression is giving up to 0.475, and ridge regression with 0.01 is alpha value is giving you 0.476 R squared value. And now we can actually find a tuned value for alpha. We can again use this and say what will be the tuned alpha value for lasso regression. So I go up again. The only thing what I have to change here is, instead of the estimated being rich, I'll give the, I can also write a function for this. Instead of giving the estimator as rich, I'll substitute here lasso and see what will be the parameter that will be obtained for best twin. See for lasso, can you see what is the difference here for lasso? The best score is obtained with the alpha value as 0.1. The best score is again 0.476. But if you want to get the 0.476 value, my alpha should be 0.1. Right? Can you see this difference? When it was ridge regression, it was ridge regularization, the best value 0.476 is obtained through 0.01. For lasso, if you see, the best value 0.476 is obtained by 0.1 alpha value, right? Can you see the difference? Yes,
Yes, sir.
yes. So I just change it to 0.1 and find that 0.476 is there. So the thing is, we know that the maximum R squared value that I can make with the without any change in the input features. If I want to change the alpha value alone, then I can say that 0.476 is the possible R squared value. After doing all the cross validation, that is five-fold cross validation is taken. With five-fold cross validation, this is actually the maximum R squared value I can get. And the alpha value which can be tuned over here is 0.1 for lasso regression, and for ridge regression it is 0.0, right? Is it clear how on the cross validation is performed, and how the regularization methods like ridge regression and lasso regression performs? So this is the thing what we have to
Sir,
discuss over here. Yes, Nasim.
sir, what is alpha, sir?
Yes, alpha, you don't, alpha is actually the learning parameter. We already discussed it, I hope.
And that I not understood, sir, clearly. That's why.
Oh, okay, okay, sorry. I thought that you know what is alpha. We treat alpha as a learning rate, right? The model parameter alpha, right? Am I making it clear? This
Yes, sir.
hyperparameter tuning. Yes. So we took this data set is actually already defined data set, and the commands are already defined. Nothing new. We usually do, right? We entirely take a new data set and use it for our laboratory exercise. But this laboratory exercise we took from an inbuilt data set. Why? Because we need to understand how the characteristics actually look. We can also use the same data set for our same code for our own ESPN click info scrapping sites where we use linear regression and polynomial regression, and to see how the cross validation things are working there. We cannot use it directly and explain you why, because we clearly know that there is no overfitting in ESPN. Why? Because even though I do polynomial regression also, of degree until degree 3 it is not fitting. At degree 4 only it is fitting somewhat, and we have Pujita said we have some other input features like strike rate with respect to number of balls and runs decreasing. By using those things, we fitted the model with the R squared value is 0.7 closely, and actually it had another method for polynomial. Right, so we tried to do overfitting there, so we cannot exactly use this hyperparameter tuning there. Why? Because there tuning there is no space for overfitting there, so the tuning values will not work directly over there. So only we showed it using a built-in data set. Right. Hope everyone have done this, and let me have a quick check on you. And if those who have not done, please let me know in which place I have to keep this.
Sir, so one doubt, sir.
Yes, Tanush.
Sir, I want to make sure that the values, the results you get on I get as different or same, sir, should be.
Come again.
The results, no, sir, the standard deviation and mean
Yes,
will
yes.
should be same to you or different to me, sir. I
It will be
mean,
same. It will be same.
but I get different, sir. But also Grid
The
set
random
in
state is
also
sorry, changes.
If you, what is the random state you fix 27 or some other value?
27 only, sir.
Maybe it will be maybe randomly sampling maybe, or it will be shuffling and taking, but not much difference will be there
So
to my
I also
unit.
I got alpha value as 0.001, sir, for research and lasso, sir.
Okay,
For
can you please share your screen?
as I can share, sir. 1 second, sir.
Already, if a random state is also used, even the alpha value will change.
Alpha will not change, sir. Learning
Yes,
rate will
alpha will
be
not change. Maybe mean and standard deviation change we can accept.
some
Alpha will change.
slightly changes.
Yes.
Sir,
Yes, Narsin.
sir, what is difference between ridge and lasso regression, sir?
Both are actually regularization techniques. In ridge regression, I said one thing, right? There is more number of independent variables and there is correlation between those independent variables, it will actually affect on the linear regression. Because according
Yes.
to linear regression, when I have more number of independent variables, there should not be any relationship between that independent variables. That is the rule. But in real time case, we cannot have like that. There will be some sort of correlation between the independent variables. So this independent variables, what it will do, it will have some effect like overfitting. Surely it will happen because variance will be there. So what these regularization techniques will do is, I stress the word regularization because we know that in spite of cross validation, regularization is also one of the technique for reducing the overfitting. This two regularization techniques, Ridge and the Lasso, what it will actually do is, the Ridge regression will by default assumes that for whatever data set it gets, it understands that independent variables may have correlation. It will understand that, and based on that, it will throw some sort of bias into the model. If we know that if bias is increased, surely overfitting will not occur because overfitting is actually the major cause of variance. If bias is increased, surely we will not have overfitting. This is with respect to ridge regression, right? So if we are throwing some bias into the model, then what will actually happen? My model will not have that much accuracy. Surely it will not have an accuracy which I actually expect from the model. So what I have to do, I need to go with respect to some other parameters which can increase the accuracy of my model. That parameter I say it will be alpha. So directly from the iteration one, I'll tune my alpha value and set a very good value for my alpha. To be in the global state, we have many kind of normalizations that and the regularization parameters. Number one is L1 regularization, other is L2 regularization, then elastic net regularization. Many things are actually available, right? This ridge regression is called as L2 regularization. This ridge regression is called as L2 regularization. Normally used when when there needs an assumption that the model independent variables will have more correlation, because ridge regression will be affected by that, by the accuracy. Lasso regression, on the other hand, is all otherwise called as L1 regularization. L1 regularization. What it does is, it is also used for the models where the independent variables will have a correlation. So instead of throwing some bias into the model, what L1 regularization or lasso regression will do is, it will throw a penalty value into my model. What is that penalty model is? For each and every correlation between the independent variables, it will throw some penalty for my y variable. So when it tries to overfit with respect to the independent variable, it immediately throws one penalty so that the y will not be exactly related to x values because of that penalty value. We can say what kind of penalty you want. Either you want a ridge penalty or lasso penalty. The value of penalty will be either L1 or L2. Or another way to write the penalty is elastic net. I will come again. Generally, there is a technique for reducing overfitting. The major technique is cross validation. Other techniques what we have is regularization, bagging, boosting. Those are also the techniques for reducing the cross validation. So that cross validation, those are also the techniques for reducing overfitting. So if I want to reduce overfitting by using regularization techniques, I have two models. Model number one is the ridge regression, and model number two is lasso regression. So this ridge regression is also called as L2 regularization. Right here, this ridge regression is also called as L2 regularization. Also called as L2 regularization. What regularization it does? It regulates the entire model by making the y value not to memorize my input x values, because my input x values by default, if they are having some correlation, that correlation should not make my y value to overfit. Now you can ask me another question, sir, if correlation is there between the input variable, then why y is becoming overfit? I'll explain that first. For example, what is correlation? If, for example, if I say x1 is equal to 2, 2, 4, x1 is equal to 1, 2, 3, and x2 will be 2, 4, 6. So what is the relation? X1 is equal to, x2 is equal to 2 into x1. 2 into x1 is x2. So if I was training y with respect to both x1 and x2, x2 is actually reading that particular features two times. Each time x1 and x2 is trained, it is memorizing the x1 value double the time each, right? So what happens? So say if I increase the number of rows, it is actually doubling the rows. X1 is also saying the same thing, x2 is also saying the same thing. So it is actually getting the same information from two different variables and actually memorizing that particular feature. So when it memorizes, it actually overfit the particular model, and that need to be avoided. So for avoiding that, we have two penalties in regularization techniques. Penalty number one is ridge regression, and penalty number two is lasso regression, also called as L1 regression. So what they will do is, if there is some independent correlation between them, that correlate for every correlation it actually sees, it will put some penalty over my y value. So that penalty will actually decrease the impact of those correlated parameters in my target variable, right? We also have a regularization equation and the model estimates for both these kinds of regression, also for ridge regression and lasso regression also. But we actually like how y is equal to beta naught plus beta 1 x comes, what is how beta naught is estimated and how beta 1 is estimated, everything we have the value. But we don't want to derive all the values for this ridge and the lasso regression also. Why? Because it is not intended actually for it. You can just understand that there are some regularization techniques, namely L1, L2. Another is also there, that is called as elastic net. So these regularization techniques will actually reduce overfitting in my model. How? It is actually assuming that my model independent variables should be correlated, and that correlation should be penalized, right? I'm making it clear now.
Yes, sir.
Yes.
Sir,
So why?
penalty means also bias only, sir. It's
Yes.
like bias only.
Yes. Penalty is for example, if I giving you some independent variables and asking you to study, there is no bias. But if I'm giving the same independent variable and putting and not making you to learn everything, if I give you, it should up to you to learn everything or drop something. It is up to the model. But I'm making you to learn only few things and making other things to vanish. And it means that I'm doing some kind of external cases or external bias and making you to learn something less. So that is actually called as bias, right? That I call as penalty.
Yes, sir. Sir, one small note and last one, sir.
No issue. How many dots you can have? Time is there.
Sir, where ridge should be used and where lasso should be used, sir, for what type of models?
Yes, when you use a linear regression model, and if you think that this linear regression model can perform even better, when you have a doubt like that, then or if you want to do a cross validation for your linear regression model, immediately you can go for a ridge regression or lasso regression. When you do cross validations,
Yes, sir.
that is, if you want to do cross validation for your regression model, you go for grid search CV and then find it. For ridge and lasso, we need alpha to be estimated. So alpha is also coming along with it.
Understood, sir.
Yes. Right. Yes, Thanush, please share the screen, Thanush. Yes, Thanush is sharing. It is loading, Thanush, please wait. Yes. Can you please go down? 0.42. Go up, go up. Thanush, please go up. Wait. 0.4. See, test size is 0.4. That is not my test size, Thanush.
What's the test size?
I set as 0.25. 25% is for testing and 75% is for testing.
In,
Right. Right. So that is what the difference.
okay, sir.
I hope that now it will come. Thanush.
Yes, sir, it will come.
It's because it will not the learning rate will never differ with respect to different people. Maybe the model the mean value may be differ somewhat, but learning rate and all will not differ.
Yes, sir, got same, sir.
Yes, thank you. Okay, those who have completed this test, put it in the chat box. Those are doing alone, you also put it in the chat box so that I can now go and check who has done and who are not done.
Sir,
Just put it.
sir, scoring means what, sir?
Scoring is actually the parameter. I have many scoring metrics starting from accuracy, precision, recall, R2. Many things are F1 score, many things. PCC, PR, kappa, many scoring metrics are available.
Why it is used, sir?
What is cross validation? In cross validation, many folds are formed, and for each fold, I'm considering it as a separate model and going to develop a model equation. So at the end of cross validation for this particular program, 5 equations are formed. In that 5 equation, which is the best equation I need to understand. By equation, I mean the hypothesis. The 5 hypotheses, what is the best hypothesis I need to identify. How to identify that? Evaluate the model with respect to any one score. So I select the scoring metric as R2, that is coefficient of determination. Right? I select the R2 score metric, and we know that if R2 score is closest to 1, it means that the model is performing good. So based on that R square metric, I am calculating the R2 for all the 5 models. Of those 5 models, which is the best R square metric we need to calculate, or what is the mean metric, mean R2, what is the mean range for all the models? We will be taking and getting.
Yes, sir. Thank you, sir.